Welcome to lecture number 33. We have been discussing about the three particle system, the n body problem. Out of that, the three body is one of the case, two body problem already we have discussed. So, in that case we were looking into the general property of the motion. So, today we are in this lecture we are looking at the third and the last property of general property of the motion. So, here this is the third property of the motion. This is total energy of the n body system is a constant. So, again we start with the equation of motion we have written here earlier. R I j whole cube now, we are taking dot product on both sides. On both sides with respect to r dot. Okay. Now, here in this equation we can, as per our the two body problem which we are discussing. So, at that time we have taken care of this kind of problem. So, this can be written as 1 by 2 d by dt r I dot r I dot r I dot and this dot product with r j minus r I, we expand it. This part we can verify 1 by 2 d by dt here r I dot r I dot. So, this is 1 by 2 r I dot dot r I double dot and plus r I double dot and this gets reduced to 2 r I dot r I double dot. So, therefore, whatever we have written here it is a true. And also you can observe that r I dot it is a dot product we are taking. So, this quantity is nothing but V I dot V I. So, that means it is a V I square term. So, on the left hand side then we have 1 by 2 times one by 2 times m I d by dt V I square. this term we have written there. Because m I is a constant, so either putting it outside or inside does not matter, and 1 by 2 also we will take it inside. So, in one step we will wind up all those things. We can write here 1 by d by dt, 1 by 2 m I v I square, and the summation sign later on we will put for all the particles. Right now we have not done this. This is the situation here right now from this equation. M I 1 by 2 we have taken outside. So, 1 by 2 v square d by dt. So, d by dt, and on the right hand side we have summation j equal to 1 to n, j not equal to I, r I j whole cube, and here r I dot r j minus r I. The same way we copy here, r I dot r j minus r I. Now, this is the on the left hand side what we can identify that this is the kinetic energy of the ITS particle in the inertial frame. But right hand side still it is not clear and we need to work out. So, what we do that we sum up over all the particles. So, now, we sum the above equation, sum up the above equation over all the particles. If we do that, so this summation d by dt 1 by 2 m I v I square, and here I equal to 1 to n, j not equal to I, now this is the situation. Okay, right hand side we have to treat it separately. On the left hand side first we will process. So, LHS we can rearrange it and write it this way, I equal to 1 to n 1 by 2 m I v I square. So, this is d by dt, and what this is the individual kinetic energy, and this term kinetic energy usually we represent it by T. So, I will write here this capital T I. So, left hand side is d T I by dt, where T I equal to 1 by 2 m I v I square, kinetic energy of the ITH particle. We have to treat the right hand side. So, on the RHS we have G times m I m j r I j whole cube, and then r I dot minus r j minus r I, and this quantity is nothing but your r I dot r I j. Now, here we have to work little cautiously. suppose the way this whole term is appearing here, we write it as another function j not equal to I, and here let us say that we write this as something let us represent it by some function p I j, where p I j is this quantity. And already, because this is because of the symbols we are using here, the subscripts we are using here, p I m I m j, r I j, r I r I j. So, this way it is just a depending on I and j, and following the earlier notation again, this can be written as j not equal to I p I j plus p j I, and 1 by 2 introducing here. So, wherever you have I, that we need to replace it by j, and wherever j is there, that we need to replace by I. So, if we do that, so the RHS gets reduced to 1 by 2 I equal to 1 to n, j equal to 1 to n, j not equal to I, and here the change will take place. So, therefore, the above equation becomes m I m j divided by r j I whole cube. We are changing r j dot r I minus r j. This is one of the term which this term is just p j I. So, this term is here, or let us first write the p I j term, and thereafter we will write the p j I term. So, let me rub it out and write first. So, first we write the p I j term from the above, g m I m j divided by r I j whole cube, then r I dot. Now, I will write it in a expanded format, or it is better to write here itself in the expanded format, one step we can save. So, this is r j minus r I and plus g m j m I divided by r j I whole cube r j dot r I minus r j. So, if we observe from this place, this term is common to both of them. This particular term is present on the both the sides. Only thing, this term we have to take care of. So, the RHS then gets reduced to 1 by 2 summation over j equal to 1 to n. Remember, these are the techniques used in space flight mechanics or the celestial mechanics, and this will help you solve many problems. Okay. This is not just unique to this one, so you will require this technique in many places. So, here we will take out g m I m j divided by I r I j whole cube, because r I j equal to r j I, the magnitude of the distance, it remains the I to j or j to I, it remains the same. So, this can be taken outside, okay. And what we are left with inside is r I dot r j minus r I minus r j dot r j minus r I. So, here we have changed the sign. This is r I minus r j. So, this we have made here as r j minus r I. Then we can observe that this gets reduced to j not equal to I, j not equal to I, g m I m j r I j whole cube, and r j minus r I, it can be taken outside the bracket. So, this is r I minus r j dot r j minus r I. We go on the next page. So, therefore, the RHS then becomes 1 by 2 j equal to 1 to n, I equal to 1 to n, j not equal to I, m I m j g r I j whole cube, and r j minus r I, and here we have r j minus one is r I minus r j, another one is r j minus r I. So, this sign we change here, this make it r j minus r I. Unnecessarily one step we have to take more. So, r j minus r I, okay. And this minus sign we will bring it here. We are changing the exchanging it. R I was here in this place. So, from here we have brought here in this place. So, therefore, the sign comes here in minus sign comes here. J not equal to y, g m I m j divided by r I j whole cube, and you can see that this quantity is one part we have missed out here. See, while working we often do the mistake, and this mistake is long standing. Here we have this r I dot, we have here r I dot. Okay. So, we have missed the sign altogether from beginning to the end. So, this is your r I dot, here also this is your r I dot. Left hand side it is okay, on the this place this is r I dot, here also we write it as r I dot. Now, this quantity we have written as p I j. So, this is okay, this part is okay, but here we need to put r I dot. So, in this place this will be r j dot. So, here this will be r I dot and this will be r j dot. So, you can see that we will have dot placed over this. Okay. So, this way okay. So, from this part finally, we are coming to this place, and once we have written this. So, this is r I j I dot sorry, this is r I j dot, because this is a vector from I to j, the symbol we are using r I j dot. So, this is your right hand side, and if you remember, for the two body problem we have used the technique that r dot r, this is nothing but so the same technique we can utilize here and solve this problem. Why this is so? Because we have started with this, and you can see that this can be written as okay. So, this gets reduced to this format. So, this is fine. On the right hand side, the stuff is now from here what we can observe that this can be written as 1 by 2 d by dt dot r equal to 1 by 2. This we have derived here. Okay. So, 1 by 2 d by dt, this is r square, this quantity becomes r square here. So, 1 by 2, and once we differentiate it, so this gives us 2 times r r dot. So, this is r r dot. So, therefore, the quantity we have here, this is nothing but r dot r, and we utilize this information here in this place, and therefore, our right hand side this gets reduced to minus 1 by 2 j not equal to I g m I m j r I j whole cube, and this gets reduced to r I j dot and r I j. And r I j here is also in the denominator. We can cancel it out, and this can be again rearranged as j equal to 1 to n, I equal to 1 to n, j not equal to y, g m I m j r I j square r I j dot. And here little bit of work, and we will be able to solve this problem. 1 by 2 1 to n summation j equal to 1 to n, j not equal to y, and the quantity here, this we can write as g m I m j divided by r I j d by dt. And what we see that the minus sign which we were carrying here, so this gets converted into plus, because once you differentiate this, so you get this quantity here. Okay, so automatically the minus sign will appear. So this is the our right hand side. So we go on the next page. The RHS then gets reduced to 1 by 2 summation j equal to 1 to n and I equal to j not equal to I m I m j and r I j d by dt we can pull outside. Okay. This d by dt, because it is a differential operator, these are linear operator basically. So, we will be able to take it outside. This you know from your basic mathematics. So, I need not get into all these things. So, we take it out of the summation sign, and once we take it out of the summation sign, on 1 by 2 we will include inside. Okay. So, 1 by 2 we have taken here in this place. So, 1 by 2 comes here, and g m I m j, and this is r I j. Okay, so, this is what we are getting. Therefore, we write this quantity on the right hand side as minus u. Where u equal to minus 1 by 2 summation j equal to 1 to n, I equal to 1 to n, J naught equal to y divided by R I J. Now, the left hand side we have got LHS we have looked into, and what we have got here LHS was dTi by, and then we have to sum it over all the particles, and okay, I equal to 1. So, summation we have to put here summation also. So, this is summation is missing here in this place, I equal to 1 to n. Therefore, we can write this as d by dt summation T I equal to 1 to n, and this we can write as d by dt t, where T I is the kinetic energy of the ITS particle. So, this is the part here. Therefore, our left hand side is d by d capital T by dt, and this equal to right hand side equal to d by dt minus u, and therefore, once we integrate it. So, this gets reduced to minus u and plus E, where E is a constant, and this is a scalar constant, because kinetic energy is a scalar quantity, and therefore, this T plus u we can write this as the E. So, this is the your total energy, and therefore, the last constant we have identified. No more all the efforts to solve this problem, more than that people have not been able to do it. So, this is the last constant you can identify. So, total of a we have got 6 plus 3 and 1 from this place, total of 10 constants we are able to identify. So, total 10 constants identified. So, total energy of the system, total energy of a system of particles, it remains constant. Means the total energy, what this is, under it is moving under mutual gravitational acceleration, and it has obviously this is moving from under mutual gravitational acceleration, and it is free from all the external forces, and moreover we are assuming that there is no dissipation of other dissipation of energy anywhere. Okay. Okay. Now, we once we have identified this constant. So, we got here a 3 scalar constants involved in this, in B again the 3 were involved, in H 3 constants were involved, and in E 1 constant is involved. So, this makes it total of 10 constants, 10 constants of equation of motion. No more we can identify, and this is the general property of the motion. Now, for n particle system, we have total 6 n constants of integration, involved, and out of this we are able to identify only 10. That means 6 n minus 10, these are the remaining unknown or undetermined constants. So, we are not able to identify, identify. So, the two particle system we have solved by assuming that one particle is heavy and another particle is quite small. So, that the center of mass can be moved to the center of mass of the main body or the bigger body. So, in that case we were able to identify those or either for the relative motion one particle is here, another particle is here, okay. And then with respect to this how this particle is moving. So, for that case we have solved and we got 6 constants, and for this where one is very small and one is large. So, in that case we have got total 12 constants. And how we have done that? This we have done that by moving the center of mass or barycenter to the main body center of mass and then applying the technique of finding the 6 other constants. So, because the center of mass motion that involves already we know that this involves 6 constants. So, 6 constants are identified and thereafter only you are left with finding out the parameter related to the orbit of this particle, because there you are assuming that it is coinciding with the center of mass of these two system. One is the heavier one and another one very small, whose mass is negligible as compared to the primary body. So, 6 constant is identified this way, another 6 constant is identified in this way, where we describe the relative motion of one particle with respect to other. So, total of 12 constants were identified in that case. But if we if we have a situation where both the particles are heavy, so in that case only we will be able to identify a total of 10 constants. 10 constants, and those 10 constants are what? They are A, B as described here in this place, and plus the angular momenta which involves 3 constant and plus energy. So, that makes it 10. This involves 1, this involves 3 and this involves 6. So, total of 10 constant. So, more than 10 constants we cannot identify even for two body problem if both the particles are heavy. Okay. If we are taking the 3 body problem. So, in the 3 body problem it is explicitly clear that only we will be able to identify this 10 constants, and rest 18 minus 10, 8 constants remain unknown. If we have n particle system. So, 6 n minus 10, these are the unknown constants we are not able to identify. So, so whatever we have solved, so 3 particles onward system it is not solvable. You cannot get a closed form solution, at least for 2 particle system. In the relative motion we have got for the relative motion considering one particle with respect to other, we have got the constants involved. Those 6 constants we were able to decipher and we were able to get a closed form solution, but for the 3 you cannot get it. So, under restricted condition we will be able to solve this 3 particle system, and there is no question of solving the 4 and other higher a system where the higher number of particles are more than 3 are involved. So, for the 3 some restricted solutions are available, and in the past researchers have done a lot of work on that, and this problem has been solved. So, we stop here and then we will continue in the next lecture. Thank you.